Mike, I think you're good. I don't think you need to attend this one if you attended that one. James, do you have a comment on that?
Yeah, no, you're good if you just attended one today.
Mike, I think you're good. I don't think you need to attend this one if you attended that one.
No. Oh, shoot.
Uh-oh.
All right. I think that I muted the YouTube recording now. So that shouldn't happen again. I guess I would find out momentarily, like right now. I'm not hearing my voice, so I must have muted the YouTube recording. All right. Can everyone see the screen with the slides on it?
Yep.
Okay. All right, we can get started. So we're just going to do more practice today. The first, let's see here. There we go. Okay, so here's the first one. So we have the following closed formula for a number sequence. An is n squared. First, give the first 5 numbers in the sequence, and then using algebra and the closed form, use algebra and the closed form to determine whether the following recursive formula is true for the same number sequence. So go ahead and take a couple minutes to work on that, and then we'll discuss it.
Oh, word. We have following close form. Give the first 5 numbers. Base of 1 is.
I think that someone's not on mute. You
Oh,
might.
my bad. My bad.
All right, let's start doing this just because we have a lot of problems. And so, all right. The first one, we have to write out the first 5 numbers in the sequence. So this is pretty straightforward. So the first one is A1, so that's going to be 1 squared. That's just 1. First one is A2. It's going to be 2 squared, so that's 4. And A3 is going to be 3 squared, which is 9. And we can do A4 and A5 as well. So, okay. And then the next part of the question is, there we go. The next part of the question is to determine whether or not the closed form can be re-expressed using this recursive form. So we're taking a closed form and trying to convert it to a recursive form. So one strategy for doing this is to try to write out an and write out an minus 1 and see if we can find a relationship between them. That's how we can move from the closed form to the recursive form. So let's write out an and let's write out an minus 1. An is n squared. And an minus 1. So this is for an n that's at least 2, because we don't have an a0. So n is at least 2. This is n minus 1 squared. And we want to know the relationship between an minus 1 and an. So let's try to simplify an minus 1. That so somehow we want to take this and we want to get an n squared term, because n squared is an. So we can rewrite this just distributing as n squared minus 2n plus 1. And that's good because n squared again is an. So let's rewrite this as an minus 2n plus 1. All right, so this is an minus 1. And then moving the minus 2n plus 1 over to the other side, we see that we actually do get this relationship. So if we move the minus 2n plus 1 to the other side, we're left with an minus 1 plus 2n minus 1 is equal to an. So does anyone have any questions or concerns about either part of this problem? All right, I think that in the homework, we've done a lot of these transformations from closed form to recursive form. So that's an important skill. So if you have any questions about it later, you can always just interrupt and let us know if you. Oh, is there an easy way to go from recursive to closed form is the question. We talked about this last week in the homework question 3. That was an example where we did want to go from recursive to closed form. In general, it may not be so easy to do that. But we do have, so there's no general answer to this question. It kind of depends on the problem, but whereas we can usually get from the closed form to the recursive form by writing out an minus 1 and trying to find a relationship, it might not be so easy to go the other way. So there's no real general remark that we can make, general strategy that we can have for going from recursive to closed. All right, so let's move on to the next question. Oops, there we go. All right, I'm going to clear my screen. Okay, so this one, let P denote the proposition it is cold, and let Q denote it is raining. Write the following in symbolic form. It is never raining when it is cold. So you can take a couple minutes to think about that, or a minute or so, and then we'll discuss. Michael, that's a good question. Let's talk about it. Like with 5 minutes left today, we can talk about how to get those finite summations. Without just memorizing them. We'll talk about how to derive them. All right, so this is question 2. So this can be a tricky one. Does anyone have any ideas? You can type it in the chat or just shout it out.
Is it like the negation of Q and P to arrow P?
Not P implies not Q.
Okay, so someone says P implies not Q. Okay. Anyone else? That's a good idea. Does anyone else have?
I swapped them. Like I have
Okay.
them in a different order.
Not Q implies P. All right. So these are all good ideas. So
Wrong, because that's not what the sentence says.
okay, let's discuss it. So it says it is never raining when it is cold. So when is like a conditional remark. When is another way to say if. So if this statement is saying it is never raining if it is cold, or another way to say that is if it is cold, it is never raining. And so if is a good indicator that we've got some kind of an implication going on. So let's start by writing out this implication. And then we have to figure out, well, what goes on, either side of the implication. So it says if it is cold. So that's the hypothesis. So it is cold is P. So P is the hypothesis that goes on the left-hand side of the implication. And then the consequence is that if it is cold, then it is never raining. So this is the consequence. And recall that Q is it is raining. So this is the it is never raining, or it is this idea of it is not raining, which is the opposite of it is raining. So that's not Q. So the first one, which is P implies not Q, is correct. And this one is not quite right because these two statements are not logically equivalent. So yeah, that's.
It also doesn't say that it doesn't say it couldn't be not raining and warm, the statement. It says it's never raining when it is cold, but that doesn't say anything about when it's not cold.
That's exactly right. Yes. So that's one way to interpret why this statement is incorrect. Because not Q is it is not raining. So if this statement said if it is not raining, then it is cold, that would be this statement. But as what's your name? I'm sorry.
Alec?
Alec made an excellent point, which is that, if we were making this statement, then it would be, it's a condition. It's a condition about what happens when it is not raining. And the statement doesn't say anything about what happens when it is not raining. It says it makes a statement about what happens when it is raining. And that's why, it makes a statement about what happens when it is cold. And that's why cold is the hypothesis. When it is cold is the hypothesis. Okay. Are there any other questions or comments about this one? Or
So
confusions?
the answer makes sense, but I was wondering, it doesn't logically follow then that you could flip it around and say, if it is never raining, then it is cold, or then it is not cold, I guess. That doesn't logically follow versus our P, then not Q.
If so,
Not
so
Q
if-
implies not P, I think, is what I had in mind.
Okay, you had in mind not Q implies not P, this one?
Yeah, and I just want to make sure that that doesn't logically follow. The answer, of course, makes sense, but how does this one work?
How does this one not follow? Okay, so not Q implies not P. Actually, this goes back to what Alec was talking about. So the hypothesis here is not Q in this statement, which is it's a statement about what happens as a result of it not raining. So this statement in particular says, if it is not raining, then it is not cold. But this statement, our statement, makes no assumption about what happens when it does not rain, or what it doesn't tell us anything about the consequences of it not raining. It only tells us about the consequences of it being cold. So that's why this hypothesis is not reasonable here. There's another thing for you to think about with this one, which is that this is logically equivalent to P implies Q. So this statement is the contrapositive of P implies Q. So another way you can think of it is, so this statement is the same thing as saying, if it is cold, then it is raining. So does the statement say that if it is cold, then it is raining? No, it says that if it is cold, then it is not raining. So that's another way to reason about this statement, why it's not correct here. Does that make sense for the person who asked that question?
Yeah, that follows. Thanks.
Okay. Okay, yeah. All right, let's move on, just because of we don't have forever. So let's go to the next one. Oh, there. Okay, so here. All right. So we're going to use a truth table in this one to illustrate the behavior of the following statement, which is written there. P implies not Q implies P and Q. So go ahead and write a truth table and show what's happening for this statement. And just to get you started, maybe I'll just write out the beginning of the truth table so it's clear exactly what you have to do here. And maybe you already know this, but I'm just gonna start the truth table for you. So whenever you need to write out a truth table to understand the behavior of a statement, then we're gonna start with P and Q. Those are the basic symbols. And then we'll write out all of the symbols, and we'll figure out what their truth values are. So we have P and Q. We're also going to need not Q because it's here, so we'll need it. And we're going to need P implies not Q because it's right there. And then we will also need P and Q. And then finally, we will need the full statement, which I'm just going to point you to that. Okay, so then we have to investigate the behavior of the statement under all conditions. So the 4 different conditions that we can have are that P is Q and Q is true, that P is Q and true is false, and Q is false, excuse me, that P is false and Q is true, and that P is false and Q is false. All right, so now you can go ahead and work out what the rest of this truth table would be. So we'll take a couple minutes to do that. All right. So there's a lot of questions in the chat. I think the main question is about the implication and when the implication is true and when it's false. So just to remind you, this statement P implies Q is false when P is true and Q is false, and otherwise it's going to be true. So for example, if P is false, the statement is true. And if P is true and Q is true, then the statement is true. So the only condition under which this will be false is when P is true and Q is false. So with that in mind, let's at least, we'll fill out the first row of the table and maybe more. So not Q, okay, so that's going to be false. And then here we have P implies not Q. Well, P is true and not Q is false. So this is the one time under which the implication is false. All right. And then we also have P and Q. Well, P is true and Q is true. So this is true. And then finally, we have this last piece, which is going to be, it's this one implying this one. And now the hypothesis is false. So when the hypothesis is false, the implication is true. So that means this is true. So are there any questions about that first row in the table? Or about anything in the chat? If anyone has any additional questions. Yeah, I mean, yeah, okay. It is a little bit unintuitive, I guess, with the one thing that I think is unintuitive is that when P is false, when the hypothesis is false, the implication is true. And the idea is that it's a conditional statement that something must happen if the hypothesis is true. And so if the hypothesis is false, then there's no violation of the condition. So we say that the implication is true. So I guess that is a little, that's what's going on. So we could also fill in the, okay, yeah, so Jonathan recommends looking at the Trooper Jones example. So in the book. So we could also fill out the last three rows. You can do that on your own. And there's something special going on here, which is that this statement, if you work out this column of the truth table and this column of the truth table, you'll find that this one is the opposite of this statement. So yeah, so you might want to do that on your own. You'll find that that this is actually logically equivalent to not P. Sorry. Yeah. P. Sorry. P. Sorry. Wait. An implication. P is true. Or. Sorry. This is logically equivalent to not P. Or not Q. So. So remember that the implication is true, provided that either the hypothesis is false or the consequence is true. If the consequence is true, that satisfies the true implies true case. And if the hypothesis is false, then we trivially, or we say that the implication is true. So this statement here, if you use De Morgan's rule, then you'll see that this is logically equivalent to not P and Q. And so what this is really saying is that not P and Q implies P and Q. So basically this implication is the same thing as not A implies A. But whatever, that's just an extra thought. So there's a lot of information going on in the chat. I think people are just discussing. So just let me know if you have a question. So we'll, yeah, just speak up if you have a question, or just say my name in the chat, because there's so much in there. I'm not sure exactly what's for me and what's not. So I want you guys to be able to have dialogue about the material. So just speak up or just mention my name in the chat if you have a question. So let's move on to the next one. Oh, Daxton raised his hand. Go ahead, Daxton.
So if I'm getting the general idea right, it's kind of like with the whole rain one. It's like if it's not raining, then we just assume that the idea is just kind of true in general, or just I'm just kind of curious why having a false hypothesis would. Do we just assume that it's true then, kind of, or?
Yeah, the implication is not being tested. So the in that last one, it was like, well, I don't remember exactly what it is, but if it is raining, then something must happen. That's the idea of an implication. And if you tell me it's not raining, then the implication is untested. And so we say the implication holds. The implication is still valid. As opposed to if the implication is if it is raining, then X is going to happen, and you told me that it was raining, but X was not happening, then certainly the implication would be false.
All right, yeah, that clears up a lot for me. Thanks.
All right, let's move on to the next one. Okay, clear my screen. We're going to write the inverse of the following statement. If Jack stays up all night, then he does not pass the quiz. So let's take a couple minute or so, and then we'll discuss it. All right, let's do this one. So the inverse of a statement. So if we have a implication, then the inverse is just going to maintain the order and negate both the hypothesis and the conclusion. That's going to be the inverse. So that's what we're doing here. So here the hypothesis is that Jack stays up all night. And so the negation of the hypothesis is that he doesn't stay up all night. And the conclusion is that the original conclusion was that he does not pass the quiz. And so the negation of the conclusion is that he does pass the quiz. So thus the inverse of the statement is if Jack does not stay up all night, then he will pass the quiz. Are there any questions about this one?
Real quick. So if instead of Q being he doesn't pass the quiz, which is what I did initially, if your Q is he does pass the quiz, so then the original implication becomes P implies not Q, that still all logically holds. The inverse becomes not P implies Q, and the logic still holds, right? Yes.
We're just taking the inverse. We can change. You can change the meaning of the statements, even if it doesn't semantically make sense. Okay, all right. So let's move on to the next one. All right. So take a couple minutes and think about this one, and then we will discuss. Jonathan? What was your question about whether the statements were logically equivalent? That whether the inverse was logically equivalent to P implies Q in the last?
Yeah, just if, because the example was Q in that instance was he does not pass the quiz. If you made your Q instead, he does pass the quiz. So the original implication becomes P, then not Q. Then that still logically holds when the inverse becomes not P implies Q. That's all. It's made sense now, but
Oh, okay.
it's all good.
You're right. So if it's P implies not Q, then the inverse becomes not P implies Q. Is that, yeah, that's all. All right. There are a lot of discussion in the chat. It all looks very substantive and good. So let's start. We're first asked if this statement is true. And so if we're either asked, is it true? Or if it's not true, show it's false by providing a counterexample. So maybe we should try to figure out whether it's true first before we think about a counterexample, and maybe in trying to show it's true, that will help us find a counterexample. So the statement to be true, there would have to be an x and a y such that for every z, x squared plus y squared is less than z squared. So why don't we try one pair of x and y just to get started, and see if one will work, and maybe after we do that, it'll help us find a counterexample. So let's try x equal to 1 and y equal to 2. So maybe that pair of x, y will work. If it was going to work, then it must be that if we set z equal to 1, it should work. If we set z equal to 2, it should work. And if we set z equal to 3, it should work. So let's see if it works for z equal to 1. So here we have 1 plus 2 squared. Is that smaller than 1? No. So actually, immediately we see that x equal 1 and y equal to 2 does not work. And it's because of z equals 1. So, well, maybe z equals 1 is the problem. So this is just one line of problem solving that we could do. So maybe z equals 1 is the problem term. So let's try another pair of xy values and see if it works for z equal to 1. So let me erase a little bit of this, but not all of it. Okay, so let's try another pair here. And the pair we'll try is x equal to 1 and y equal to 1. So maybe that'll work for z equal to 1. So we try z equals 1, and well, we would have x squared plus y squared would be 1 squared plus 1 squared. Is that smaller than 1? No, it's not. So again, z equals 1 is causing problems. And so now we just tried the smallest possible sum of squares we could by using x equal to 1 and y equal to 1. So this is telling us that maybe z is providing us a counterexample. So if we want to verify that this is a counterexample, let's create the negation of the statement and then show that this value of z satisfies the conditions for the negation. Then it would be a counterexample. So if we take the negation, it becomes for all x in A and for all y in A, there exists a z in A, that's a z in A, such that x squared plus y squared is greater than or equal to z squared. All right. So what we can do is make z equal to 1, and then try every pair of x and y values. There are a lot of different pairs, so this is something for you to do on your own, but for every possible pair of x and y values, then the sum of squares is always larger than 1 squared, than 1. So this value of z satisfies this statement. So for all x and y in A, there does exist a z such that this statement is true. Therefore, the negation of the statement is true, and therefore we have a counterexample. I see that there's like paragraphs of text in the chat.
Yeah.
I don't know. Does anyone does anyone want to discuss this? Or if you have a question for me, let me know.
So it
Hey,
looks
I
like
have a question. Oh,
Summarize the chat. If you want.
Let
Let other people.
my question is, I thought as long as you can provide a counterexample, then this is false.
That's true. Yes.
Then
I have a question then. For an exists, like there exists an x in z such that y equals, or such that, x is greater than 1. I can't just say, well, 0 is not greater than 1. I have to prove logically that the negation is true, which is for all x in z, right? What he's saying.
That's for a there exists. So you're right. If you have a statement which says, let's say there exists an x such that x is greater than 0, and you want to show that that's not true, then you would have to show that for every x, then x is less than or equal to 0. But in this particular statement, we don't have to do that.
Well, but we kind of do. You're just arguing that you don't have to examine other cases because 1 squared plus 1 squared is the smallest possible value. And like, it's true that you can pick an X and pick a Y and then find one Z that doesn't work. And now you've scratched off that X and Y case, but that doesn't mean that another X and Y case couldn't be true.
Well, we only had to find one Z. Remember that.
No, I agree with that. I agree with that. But I'm saying that finding one Z that doesn't work for a particular choice of X and Y does not
is not
mean that
sufficient.
other choices of X and Y are also.
Right. Yes, that is not sufficient. You need to check for every pair X and Y.
Jonathan,
that this particular Z works.
more efficiently than I am.
Say that one more time. Sorry, I missed it.
In chat, Jonathan said it more succinctly than I'm capable of. He says if it's a for all predicate, we have to find one counterexample case. If it doesn't exist, we have to prove it for all. But they're both in here. So I'm saying to prove the whole statement, we can't just find one case of X and Y and one Z. That's all I'm saying.
No, you have to find, in this case, because there exists an X, Y for such that for all Z, the statement is true. We now have to find one Z such that the statement is not true for every X and Y pair. Yeah. So in this case, it's kind of useful to write out the negation of the statement and to try to prove that the negation is true.
I have a question that
Yes.
Can we not just find a counter example and say this is false?
And that's actually what we did. So we found the counterexample, which is Z equals 1, and we showed that for every pair X and Y, the statement was false. So that means that there is no pair X and Y such that for every Z, the statement is true. And so we have found a counterexample such that the statement is false. It's a little bit confusing.
So why would it be so long? Like, can I just make X equal 1, Y equal 1, Z equal 1, and then say it's false, and then I just say the whole statement is false?
Almost. So we need this to not work. We need to find a Z such that it doesn't work for every pair X and Y, because not just for one pair.
Okay. But that still wouldn't be too long, to be honest.
Yeah, it won't be too long. So you find Z equal 1, and then you have to check every pair of X and Y values that this inequality X squared plus Y squared is greater than or equal to Z squared. So you have to do X equals 1 and Y equals 1, X equals 2 and Y equals 2, X equals 3 and Y equals 3, X equals 1 and Y equals 2, X equals 1 and Y equals 3, and X equals 2 and Y equals 3. And once you've checked all those cases, you're done.
Oh, you need to check all of them?
Yeah, so it's easy. You don't really have to do it here because it's pretty obvious that whenever you take two numbers and you take their sum of squares and the numbers are all greater than or equal to 1, that their sum of squares will be greater than or equal to 1. So if you argue that, that's fine. You don't technically have to check every single case. But if you want to be very rigorous, you somehow have to argue that for every X and Y in 1, 2, and 3, X squared plus Y squared is greater than or equal to 1.
So on the homework, I just did one of them. I didn't list all of them.
Well, I'm not sure exactly what problem you're referring to, but every problem is a little bit different. So we'd have to look at the problem. So, all right, let's.
One more. Is it sufficient to just say that, to just show that the negation is true?
Yeah. Yes, and that's actually what we did. we
Yeah,
found.
that's what I'm saying. Like, we could just show the negation is true without checking every pair.
Well, the negation, if you look at the negation, it says for all x in A and for all y in A, there exists a z such that x squared plus y squared is greater than or equal to z squared. So you have to find the z and then show that it satisfies this condition for every pair x and y. So
Okay.
'cause that's the negation.
Right.
Yeah. All right. There is an excellent discussion going on in the chat.
So there was one good question that was brought up in the chat, and they were asking if they had this question on the quiz, is it sufficient to just state that the counterexample would be z equals to 1, or will they need to go through the steps to prove that z equals 1 is in fact the counterexample?
My personal opinion is that you should show in this case that for every x and y in the set 1 through 3, that x squared plus y squared is greater than or equal to 1. And you don't need to actually write out, you don't need to write out every single combination. You just need to argue that if two numbers, x and y, satisfy that they're greater than or equal to 1, then their square is definitely greater than or equal, the sum of their squares is definitely greater than or equal to 1. So I'm not saying go out and write all 8 or whatever cases. I'm not saying you need to explicitly write out each one. Just make sure you argue algebraically that if x is bigger than 1, bigger than or equal to 1, and y is bigger than or equal to 1, then x squared plus y squared is bigger than or equal to 1. All right. Anything else, James, that from the chat that we should discuss?
I think we kind of covered a lot of the other stuff.
All right. So I think we end in 2 minutes. So there are other questions here. I think there's only one more that we didn't get to, but we have 2 minutes, so let's take a quick look at it. I think that was the last one that we were supposed to get to. So let's take a look at that really quickly. Oh, here it is. Okay. So clear the drawings. All right. So we can do this. We're supposed to write out the closed form for this sequence. These all kind of look like powers of 2. So 5 is close to 4, 8 is close to 7. Oh, this is a power of 2. This is 2 cubed. 4 is 2 squared. Okay, so, and 17, that's close to 16. 16 is a power of 2. That's 2 to the 4th. So, so that's telling us something. That's telling us this has something to do with powers of 2. So if you look at 1, it's 2 to the 1st minus 1. Interesting. Okay, and then 5 is 2 squared plus 1. Oh, well, okay, that's weird because we just subtracted 1 from the square, and in the second term we're actually adding 1 from the square, but let's keep going. A3, that's 8. 8 is 2 cubed minus 1. Oh, okay, so when we had 1, which was odd, we subtracted 1 from the square, and when we had 3, which is odd, we subtracted 1 from the 2 cubed, and when we had an even number, which was 2, we added 1 to the 2 squared. So let's do one more, a to the 4th. Okay, a to the 4th is 2, it's 17, and that's 2 to the 4th plus 1. Okay, so again, we had an even number, which was 4, and we took 2 to the 4th, and we added 1. So when we have an even number, we add 1 to the power of 2, and then when we have an odd number, we subtract 1 from the power of 2. So let's do one more just to see exactly what's happening. Here's A5. A5 is 2 to the 5th minus 1. So it's an odd number, and we're taking 2 to the 5th, and then we're subtracting 1. So for every odd index, we're going to subtract 1 from our 2 to the power of n. So in general, the sequence is an is equal to 2 to the n minus 1 if n is odd. And then if n is even, it's going to be 2 to the n plus 1. And I'm sure that some people are commenting in the chat that there's a simpler way to write this. So minus 1 to the n is going to be negative if n is odd, and it's going to be positive if n is even. So we can rewrite this instead of this, but this is fine, but you can rewrite this in the following way. We can rewrite this as, I'll just write it out over here. A to the n, a sub n is equal to 2 to the n plus minus 1 to the n. Okay, so when n is even, that's going to be 1, and when n is odd, oh, sorry, this is a minus 1. When n is even, that's going to be 1, and when n is odd, that's going to be minus 1. So as Michael points out there. So that's all. There's some other questions in here. James, am I missing anything that I should be telling everyone?
No, I don't think so. Yeah, I think you're good.
Okay. I hope you all have a great weekend. That's all. I'm going to stop the recording now.
Oh, I guess from 2 to 4, I'll have a review session.
Oh,
so if
yeah.
you have more questions on this material, stop by from 2 to 4.
All right.
Thank you.
Stop.